Stars. For millennia, these bright little spots in the sky have kept the observer both fascinated and puzzled. Living in a complex nature of diversity and unpredictable changes, man naturally gazed and wondered at the rather simple cosmos harmoniously subsisting on the celestial dome. But 150 million kilometers away from Earth, a very peculiar star punctuates the rhythm of life: the Sun. Like any other star, the Sun is a massive ball of burning gas radiating tremendous amounts of energy. For most of their lives, stars fuse the hydrogen located in their core into helium, and the outward radiative force created from such processes counterbalance the gravity that would otherwise drive them to collapse. From such equilibrium arises the apparent stability of stars. Stars' lifetime can range from several million to a few trillion years. And more massive stars burn their fuel at a much quicker rate, giving them a much shorter life expectancy. When a massive star runs out of hydrogen in its core, it goes through a series of contractions and expansions, leading to the creation of heavier elements such as oxygen and carbon, the very same elements you are made of. In its last breath, the star explodes and gives rise to one of the most beautiful events known in the cosmos: a supernova. These magnificent explosions eject the hot gas of the dying star at tremendous speeds and leave behind what remains of the core. Such phenomena are believed to occur about 3 times per century in our galaxy, but only a handful of them are visible from Earth. Some very remarkable relics of such explosions can be observed in the Cassiopeia constellation and in the Taurus constellation, where the Crab Nebula is known to be the remnant of a supernova that occurred almost 1,000 years ago. At the center of these nebulae, a very peculiar object has caught the attention of astronomers: a neutron star. When a star with a mass 10 times greater than the Sun's dies, a remnant survives in the form of a small, compact ball mostly made of neutrons, the same particles that make up atoms. Imagine the Sun compressed into a sphere the size of Manhattan. A teaspoonful of neutron star material would weigh about 1 billion tons. Observing such objects is not an easy task, but scientists were able to detect a few of them thanks to the so-called lighthouse effect. As it rotates around its rotational axis at speeds as high as 700 rotations per second, a neutron star can also emit jets of particles and radiation at its 2 magnetic poles due to the intense existing magnetic fields. If these poles are not aligned with the rotational axis, the beams span the sky and regular pulses of electromagnetic waves can be observed from Earth if it is positioned in the path of the beam. We call this very specific type of neutron star pulsars. Although 1 billion neutron stars are thought to populate the Milky Way, only a few thousand have been detected so far. This gap can be explained by the fact that most neutron stars have been existing for billions of years and therefore had time to cool down, thereby significantly reducing the detectable emission of electromagnetic radiation. However, another scenario is possible. As most stars exist as pairs in a binary system, if one of them happens to be a neutron star, it can accrete gas from its companion and increase its own mass. If its total mass exceeds 3 solar masses, it can no longer withstand its own gravitational force, and it collapses into one of the most exotic and fascinating objects in the universe: a black hole. First predicted by Einstein's general relativity, black holes are without a doubt some of the most mind-bending and strange objects nature has to offer. When a massive star collapses, its core may reach the point where its mass is constrained to such a small region of space that its gravitational field prevents any form of light to escape its grip. Although quite peculiar, black holes are very simple to describe. At the very center of a black hole, a point of zero dimension and of infinite density, called a singularity, attracts all light and particles that crosses the event horizon, the dark surface of the black hole that marks the point of no return for any light or particle that cuts across it. Outside but close to that surface, the gravitational force is strong enough to bend the trajectory of light, to create a bright ring called a photon sphere. If any matter or star wanders too close, it will be ripped apart by the strong gravitational forces, and an accretion disk of hot gas orbiting the black hole will be produced. Such accretion disks are among one of the features that allow scientists to detect black holes in the universe. Such phenomena can also generate jets of particles traveling close to the speed of light. These beams of particles can sometimes extend over several thousand light years and hint at the existence of a black hole at the source. However, scientists can also detect the presence of a black hole by observing the trajectories of nearby stars. In this scenario, stars are seen to be orbiting around what seems to be an empty patch of space. By carefully studying these orbits, astronomers are able to calculate the mass of a black hole. In fact, this technique has been used to infer the existence of a very particular black hole. Sagittarius A. 25,000 light-years away from Earth, the center of the Milky Way hosts several stars that seem to be orbiting around an invisible object. From their trajectories, the mass of the black hole was estimated to be around 4 million solar masses, yielding to a diameter of almost 50 million kilometers, equivalent to 1/3 of the Sun-Earth distance. As of today, the detection of gravitational waves has brought more evidence supporting the existence of these fascinating objects, and their mystery is slowly being unveiled.